Thanks. Oh, hi, folks. Thanks. Coming in. Thanks. My name's Lyndsay. I'm a principal consultant with Equal Experts. For the next 45 minutes or so, I'll be giving you an experience report of some really interesting lessons I learned when having the best time of my life working on a massive robotic system at a large e-commerce client about a year ago. And it was a very, very fascinating system to work with, very, very complex. I'll hear more about it over the next 40 minutes. What's the problem that we had to face? It was a cyber-physical problem, which is what this kind of talk is all about. And we're going to go through why the combination of software systems and physical systems, when they interact, causes particular challenges and recommends some approaches for addressing those challenges. And then it draws out some of the things that we've learned by addressing those challenges that we can then apply to either regular systems or broader cyber-physical systems, including things like the Internet of Things. When I talk about cyber-physical, I'm not talking about the cyber-physical. It's much more mundane. Sorry if you're disappointed, but no Cybermen are going to be mentioned after this slide. So the kind of cyber-physical system that we're talking about are these kind of robots. So on the most advanced kind of level, it's a Cardo's hive. So we got robots automatically picking things to go in a shopping basket that someone's ordered online, ranging to an automated production line for making bread. Also includes things that you see in airports when you put your suitcase on the scale and off it goes behind a big screen and ends up in this massive matrix of conveyor belts. To simple sorters that put a box on one end, takes it through the warehouse and works out which part of the warehouse it should drop it off at the other end, hopefully to go onto a truck. So these are the kind of cyber-physical systems that my talk is all about. Across all those different types of systems that I've already described, coming in through, folks, there's plenty of seats, they share various common characteristics. The kind of principal characteristic is that they have deep connections and deep kind of entanglement between the physical systems and the software parts of the systems that are processing that physical volume. And this intertwining happens kind of in multiple different places. So for instance, in the sorter, it happens when people receive products into the warehouse and they store them, that are then later picked. It happens when people print out a label, stick it on a box. It happens when people take the box and put it on the sorter. So all of these touch points where people are working with software and working with physical volume, where you see these interactions happen. Secondly, cyber-physical systems aren't just processing digital volume. You're not just having to think about HTTP requests or events being processed or data being transformed. You're having to think about all those things as well as physical volume, actual physical things that you can see and touch going through a system that interact with each other, interact with the system, and cause all sorts of problems. The third common factor across these systems is flipping people. Generally, don't work with people because they just complicate things so much. Particularly if you're working with people who are working with physical products that then interact with software, it causes all sorts of problems, particularly when there's a high amount of repetition, because software exists, right, to solve highly repetitive tasks that humans aren't that good at doing. However, there's some cases still where we do need humans, we do need people to interact with these systems. And generally, in this case, those people are picking up a box, working out where to put it, and then leaving the software system to do the rest of the job. And those small touch points can lead to all sorts of problems. So this is the types of cyber-physical characteristics we're having to deal with. Right, this is a short video of the real thing, just to give you a bit more of an idea of what we were dealing with. And we've tried to make it more exciting by mounting a camera on a box as it rides the sorter. And what you'll see happen is the box going up some conveyors and then moving around a bit. There's lots of conveyors that interconnect. And this is just one box riding up the conveyor. So what you need to imagine is that at the same time as this one box, there's hundreds of other boxes that are all kind of crisscrossing and interleaving. At some point in the video, you'll see some big red lights flashing, and that's the sorter the carton going through a very important part, which is called the scanner. And the scanner has lots of high-tech lasers and very low-tech cameras that take photos. So it's measuring the box, taking photos, working out where all the labels are, doing image processing on the labels, and then it's working out where to send it next. So hopefully we'll see some video now. Okay, so it's been loaded, the box is riding around. There'll be other boxes running around if this was happening in real life. It goes through the scanner, and you'll notice it's passing lots of things on one side. Those are diverts to other parts of the warehouse, ideally trucks that the box could be then loaded onto. The sorter is one big loop, kind of figure of 8. So if it can't find where to put the carton, then it'll just keep going around until the software system has worked out where it should ultimately divert it. So hopefully you get the idea of the kind of system that we're looking at. Now, this system was hugely fun to work with. I got to kind of put a high-vis jacket on every day, walk around the warehouse, pick up boxes, stick them on the sorter, see them ride around, and do lots of fun problem solving. But the system didn't just exist for my pleasure. It wasn't just a big toy. It existed to solve a business problem. And the business problem that this client had was that they allowed people to buy things online for their home. Massive range of things. It could be just a set of light bulbs, or it could be a jacuzzi, or a sofa, or a bed, or a table. And they wanted to be able to process all these orders very, very quickly. So you could buy it and then have it delivered the next day or in 2 or 3 days. They wanted to do that very, very cheaply. And they wanted to do it with minimum problems. So they wanted to ensure that when you ordered something, it got to you with no breakages, no kind of damage, and it was the right thing that you had ordered. Those two things, so doing kind of perfect orders fairly cost efficiently, is something you can do just with people in a warehouse. You can have people, well, unfortunately they're fairly low paid, but these people can effectively follow a process, pick the right box, put it on a truck, and that works. The problem was doing this at scale. So in order to be profitable, they needed to process upward of tens of thousands of orders every day through one warehouse. And that's where the sorter came in. So having an automated sorter allowed them to scale this whole delivery process and make it cost effective. They had already bought the sorter when I got involved, but they're having problems integrating it with a multitude of software systems that their company operated. Plus, they needed help then tuning it once the sorter was up and running and processing physical load. This is a diagram of the architecture of the flow of the sorter and highlights the different stages that something went through and different physical and cyber components involved. So to start off with, an order gets kind of placed by a person through a website. A person in the warehouse will have received a box that is going to be that actual product that someone's going to buy, and they'll have stuck it in some part of the warehouse. People have also thought about trucks, because trucks are physical things, right? You can't just magic up a truck to take your order somewhere. You need to plan that ahead. You need to tell the carrier that organized the trucks how many trucks you need, what time you need to arrive at the warehouse. That kind of thing, it takes planning, and it's done by a human, but through a software system. So once an order is placed, it then needs to be picked by somebody working in the warehouse. They're going to find the cartons. They'll be directed to the right place by a software system. They'll look at the label, scan the label on the box. That generates a new label that says, this box is for this customer. It's going to go on this truck. And at that point, there's probably some software systems trying to work out, should we change which truck it's going to go on to kind of further optimize its delivery. Once the combination of carton and order and product and truck have been kind of made, that kind of union, information starts being processed by the software system to go to the sorter. So there's lots of events now that are happening throughout the system as a result of these physical and cyber interactions. The trucks are arriving at the warehouse, and they need to know where to go, because the warehouses typically have anything from 10 to 30, 40 different doors that you can put a truck on. And those doors are each connected to a different part of the sorter. So again, a physical interaction. There's also a software component here, because people are needing to tell through a user interface the sorter what truck is at which door. So when the sorter works out that this carton is for a particular truck, where to send it. So again, more interactions, more events to go to the sorter so it can process the cartons effectively when they arrive. Finally, the carton gets put on the sorter so it can do the magic of routing it. That involves going through a scanner, which we saw earlier, taking lots of photos, measuring it, determining the size and the weight. More events go through the kind of the sort of pipeline, so it can ultimately work out where should it send it in the warehouse, where's the right place to send it. Ideally then, the carton gets diverted to the truck, gets loaded, and more information gets generated, more events that can give us feedback on how well the system is working. We also now see the word jackpot tool. And jackpot is not a good thing in a warehouse. So it's an industry standard term that's unfortunately been named. It's also a term is used called hospital pass or hospital lane, which is probably a bit better. So a jackpot lane is where things go if the sorter can't work out where to put them. And you don't want lots of jackpot. In this case, you want jackpot to be very, very low, almost non-existent. But it's there for a reason. So the sorter is trying to work out where to send it, which may be to the jackpot tool. So that's the whole system. We're going to go through now the complexity of just the kind of the last two stages. So the sortation part of it. But once something has been put on the sorter, it goes through these steps. So the sorter will detect it. So it will go through the scanner. The scanner will recognize that a carton is entering it. It will use the lasers to work out dimensions, take lots of photos from 6 different sides to firstly locate the barcodes, then try and understand if it recognizes those barcodes. From those barcodes, it'll then try and extract IDs and work out, are those IDs ones that it's been told about from all these events that have been sent to it from earlier? If it can take those IDs and resolve them to a unique carton that it's been told about, and then work out, okay, this carton, where have I been told it's going to be sent to, which truck has it been assigned to? It can then make a sort decision and divert it to that truck. If it can't do any of those things, for whatever reason, then it's going to go to our awful place, the jackpot lane, which is going to make people very sad. And the problem that we faced was we got the system up and running, all integrated, which is great, started processing around 5,000 cartons a day, and about 30% of them went to jackpot. Yeah, it was a bit painful. And you'll see some photos just to see kind of what that amount of pain looks like. It's useful to have kind of different failure modes defined and measured, and we categorize these failure modes in these ways. So if the scanner for any reason couldn't read the label, identify the label, or map the label to kind of IDs, then we call it a no read. If for any reason it went to jackpot, it was a jackpot failure. You'll notice it's a big loop, okay? So what can happen with that big loop is if the carton is successfully identified and it knows where to send it, but it gets to the point where it's supposed to be sending it, and that part of the sorter is actually full. Perhaps the people at the bottom of that part of the sorter have a problem taking the boxes off, so it all backs up. The sorter can't send it down because it's full, so it sends it round the loop again, goes to the scanner, round again, and if it's still full, it will send it around a set number of times. And you don't want a carton riding around infinitely, because that could be quite bad. So it decides a certain number of repetitions it will send us to jackpot. So that was also a failure mode that we had to kind of track and be aware of. So a slight kind of side note on the whole jackpot term. Is it a failure mode, or is it actually a beneficial thing? The Toyota production system, it has 12 pillars. And one of those pillars is something called Jaduka. And Jaduka is a really important concept because it's something that TPS kind of realized back in the day when they had automated weaving systems, that if they could automate the detection of a problem in the system, and if it could stop the weaving and tell the operator that there was a problem, it was really great because it saved waste. It prevented a whole kind of woven fabric being produced that had an error. So it saved waste material. It stopped the machine being used to produce something defective. And this is what we see kind of happening here. This is Jaduka in action, because the jackpot lane, the whole jackpot system, is designed to detect an error as early as possible that is going to be sent then somewhere that a human operator can then process. It means that the rest of the sorter is not taken up with a defective item, and ultimately it prevents that defective item, that carton that can't quite work out where it's supposed to go, ending up at the wrong customer. Because that's one of the failure modes that we had. So a certain amount of jackpot is actually a good thing, because it's helping reduce the impact on customers. The problem with Sudoku and problem with Jackpot is it can get to a certain level, like 30%, where it starts impacting the whole system. It starts causing the whole system to back up and cause problems to cartons that actually are fine to get to the customer. It causes things to kind of get delayed. And that was the problem that we faced. We had about 5,000 plus cartons riding the sorter every day, mass amounts of them ending up at Jackpot, and it was basically becoming an unsustainable situation. But before we dig into that a bit further, there's one other kind of metric that we track. And we track these metrics. We get a report every half hour that would tell us the performance of the sorter. And every day we had a cross-functional meeting where we look at the previous day's statistics and try and work out, are we getting better? So are we lowering our failure modes? Or are we improving our utilization? Because sorters are really expensive. They cost millions of pounds to make and install. And the labor of people is actually relatively cheap. So in order to make a sorter pay for itself, you want to get as much of the cartons that the warehouse is sending out onto the sorter as possible. The utilization was really, really important. And that was another problem that we're having. We weren't getting it high enough. So we were looking at these forward numbers every day, scratching our brains thinking, how are we going to make this system actually efficient? We spend a lot of money on it. We need to improve it. Now, the reality of the situation is each day, the people working the sorter, picking the boxes, putting them on the truck, they're not thinking about no reads, Jackpot, recirculation, utilization. They have a truck that's going to be leaving the warehouse in half an hour or a few minutes. And they know if they don't get this box on that truck, it's going to miss the date the customer was expecting it to arrive by. The customer's going to be unhappy. They may not buy again. So this is an added pressure for all the people that are working in the warehouse and for the team that I was with, that each day we had to make sure that we got as many of the items on the truck that they're assigned to as possible. So with that kind of context, let's go through now a bit about the actual chaos that we are facing and how we diagnosed it and then work out what we did to tame it. One of the challenges of working with cyber-physical systems is that errors can be introduced at multiple different levels of the system. And each of these different layers, they interplay. So a small action by a human can interplay with a small defect in the kind of actual mechanism of the system. And those two things combine to cause other problems. And trying to unpick all these and work out what are the main contributing factors and how can we fix them is a real nightmare, as we'll see shortly. So to help us get down from 30% to kind of very low, like 2 or 3% Jackpot, we had to break it down into kind of further causes. And this was something that our systems could do for us. We could tell what type of Jackpot failure it was. So for instance, if a carton, it could be scanned and the system could recognize the tracking IDs, but it didn't find the tracking ID in its database of cartons it knew about, then we called that a carton not found. Similarly, if it found the carton ID, if it could have scanned it, found it in the database, but it couldn't find a corresponding truck that matched up with that carton ID, then there was no destination for it to go to. So again, another way of sending it to Jackpot. So this breakdown was really helpful to us because it started to decompose the problem that we're facing, trying to slice up that 30% Jackpot into kind of lower levels. It meant on a half-hourly or daily basis, we could have a look at a pie chart that showed all the main causes of Jackpot like this. So this is great. You think, well, it's really obvious now what to do. Just go after the biggest segments of the pie, fix those, job done, right? It would be easy, except on a daily basis, this is what you're kind of dealing with actually in the warehouse. So after about, an hour of the sort of operating, just this area, these are all the cartons that have come to Jackpot. And you've got to get them on a truck that's leaving in half an hour. To make matters worse, this is 2 floors up from where the truck is. To get them down to that place is a lift, which goes really, really slowly. So you can imagine the stress of the operators when they're faced with this amount of volume at Jackpot. Now, on the far side, you see some examples of what we call no reads. So you're faced with all these items, you're trying to diagnose what caused these items to fail. Was it a software problem? Was it a human problem? Was it something else? Is it because the label is a bit wrinkly? Is it because the label's been applied to a curved surface? Or is it because of the image that was generated by a software system is too blurry? It's very hard to tell. It's even further hard to tell when you start thinking of all the different possible problems just for one main issue, no read. So this is a simplified problem tree that we created to help us diagnose exactly what caused a no read. And you can see it's a multitude of different physical and cyber interactions that are happening here that lead to a no read. Having this kind of tree took a bit of time to build up, and it was a really useful way of training people to diagnose something so we can get more information on what to fix next, what to go after. So if you picture that tree, that's just for one of these segments of the pie. The other segments of the pie had similar trees. So it's like an explosion of causation. And that was a real stressful thing to deal with. And we had to think hard, try and pick from different toolboxes that we had to figure out how we're going to solve this. The other reason it was so hard, because on a daily basis, you were faced with this amount of product. So diagnosing a no read, you would take one of those boxes to work your way through that tree. For one box could take about an hour, because you were looking at different systems, looking at images from the scanner, looking at logs from all the kind of events the sort of was processing, trying to marry up, what did the scanner see, which box was it trying to track? And doing that times like several hundred boxes proved very difficult. But we're having to do that in order to work out which one of those parts of the tree do we need to kind of go after first. At the same time, you're faced with this constant pressure that you've got to get the box on the truck on time, otherwise people are going to be very sad. The final kind of problem that we were facing is that no day was ever the same. You would think that in a system with a high throughput, a lot of software, you're going to have some stability in the kind of errors that you're seeing. Well, unfortunately, it's a cyber-physical system. Humans are very, very fallible. They're very, very variable. And so are machines, it seems. So each day we saw jackpot numbers varying wildly. We also saw the different main causes of jackpot varying quite a lot. And this just made it kind of very difficult to say, we should go after this, we should go after that, because it would vary each day. So what did we do? How did we take all this chaos and tame it? What kind of approaches really helped? Oh, sorry, I missed a slide there. Nope, okay. So I think the most important thing that we kind of did to start off with was focus on observability. And I've worked quite a lot with platform teams and helping teams manage production issues much better. And one of the things I learned from that experience was just how important it is to be able to observe what your system is doing. And we had very good observability of the software components. We had the kind of Grafana working really well. We had Kibana, we had Datadog. We could see all these events going through the system. We understood what orders were being processed, which trucks were being assigned. And that was great. But we needed then to apply that to the physical part of the system as well and join the cyber and the physical together. So we had to start working out what different tools did we have available to us. So like in the middle, we had information from the sorter itself. It had its own control and reporting system that told us what cartons it had scanned and what events it was receiving. So we had to marry up the information we were receiving there from other systems. We had the cameras that were based around the sorter as well, and they could show us when did a particular box go through a scanner and what other boxes were nearby it. Were two boxes interacting in some way that caused these problems? So we had to learn how do we pull together all our observability tooling in order to kind of diagnose these problems. And as we did that, we realized that when you're dealing with cyber-physical systems, it's really important to think about observability from a whole system perspective to make sure you can observe every part of the process and understand all the different touch points in that process. It's also important to make sure you've got enough history so that when you have a problem that you're looking at, because of the boxes going out every hour, sometimes we would have the details of a problem that we wouldn't get to investigate for a few days. I remember looking at some boxes that weren't scanning properly. We had the photos of the box that somebody had taken, and we wanted to find these photos in the scanner's database of images that it took. Now, the scanner is an embedded system working on a computer that's based near the sorter, and it didn't have much memory, so it deleted all the photos from the previous day. which was great until you wanted to look, 3 days ago. So that was something we had to fix quite quickly. It's then important to recognize or determine, how do you join up these different identities that exist across your system? So how do you work out, which person picked this product, which person inducted it, where did they induct it, and where did it go after that? Where did it actually have the problem? Because these interactions in terms of who did what, who scanned it with what device, they all contribute to the actual cause. As we start looking at all these different problems and this information, it became important to share these views on things with different people in the system. So making observability tooling easy to access was another thing that was really important. When you're working in a warehouse, particularly if you're using cameras to record things, you have to be very mindful of privacy, and particularly in places like Germany, where there's even stricter rules there on where you can film. So trying to plan for how you can capture images of people working or products riding a sorter takes extra consideration. With all this information that you're trying to kind of log as well, you need to be careful about GDPR, because it's important to kind of know which truck is something going on, what's the postcode it's going to. That starts kind of bringing in PII as a problem. So you want to limit how much personal identifier information is leaking into your logs. So these are all different factors you need to think about when you're considering observability. Identities also became a kind of a very important issues for us to consider, and the relationships between those identities. So as we were diagnosing these problems, so we started realizing that it'd be much, much better if we could map all these different items and kind of identify how they related to each other. So one particular problem that we had was when a carton was riding the sorter, we wanted to know, where did it actually go? And sometimes the only evidence that we had of where it actually went was some video footage we had from the sorter and the cameras. And it's hard to tell, which part of the sorter did a box go through, because lots of the sorter looks the same. It's basically a big loop, and it's hard to tell one part from the other. Apart from it does have these little IDs kind of printed around it. So knowing a mixture of physical IDs and software IDs, trying to map all those together was also an important thing for us to understand. I think one of the kind of biggest advances that we made was following this principle again from TPS, so the Go, Look, See principle. And that talks about the importance, in order to understand a system and a process, to actually go and embed yourself in it. So I spent a lot of time actually going down to the warehouse and working with the people that were operating the sorter, spending time in the jackpot area and looking at what they were seeing and helping understand how did things come to be there, and working with the jackpot operators to help them understand and diagnose how things were kind of arriving there. When we set the system up and had it kind of processing all this volume, we knew that there were going to be problems, and we knew from other warehouse locations that there was different types of jackpots that would happen, but we didn't fully understand how you would diagnose them or what the different factors were that contributed to them, particularly as this was the first time this kind of system had been set up in the UK for the client. So a lot of the problems we were facing were unique to the UK, and there's different carriers, different barcodes. But being actually on site, looking at physical boxes and doing the diagnosis with your own eyes made a massive difference, because it helped really internalize the whole domain that we were working with. And that domain knowledge allowed us to build up models that we could then use to work out which are the causes that we need to kind of go after next. The next thing that we used was data. So once we started breaking down these different failure modes into kind of root causes, we could then work out what percentage of jackpot were those causes contributing to. And if that jackpot proportion was going to cause those cartons to miss their deadline and so be late for the customer, we could extrapolate what the impact on the customer lifetime value would be. Let's imagine that the customer got the carton late, they didn't buy from us again. That could turn into a monetary figure. And we could then use those monetary figures to work out, if we fixed just one issue, what kind of saving could it make over a course of a year? Also, as we worked out which were the main kind of problems and the kind of single causes that contributed to the jackpot, we could then identify which teams owned the component that we needed to fix. And were they software teams, were they operational teams, were they third-party suppliers? So we could start working with those teams to help come up with solutions. We had a very big spreadsheet like this that showed all the different causes and different teams. And this is great because it gives you lots of opportunity to reduce jackpot and fix things. But the other lesson we learned with this is that because it's a very complex system, you don't want to be fixing too many different things at the same time. So we kept focusing on just what's the one biggest thing we want to go after, or the one easiest thing that we can fix in the next couple of days. So just going over after one or two things at a time, that allowed us to slowly chip away and start reducing the complexity of the system. That data also started showing us which teams owned the different problem areas that we're facing. It wasn't just technical issues that were causing the problems. And that was something that people believed initially, that most of the problems were due to the tech. It wasn't quite integrating properly. But our data started showing that actually a lot of the problems we're seeing were more to do with operational issues or maybe mechanical design issues. And those kind of two teams, the mechanical team and the operational teams, they generally weren't used to solving problems in this kind of way or working with each other and with the software teams to help improve the system. So we started getting together much broader cross-functional teams, people from tech, from operations, and from mechanical engineering. So together look at the problems that we're facing and work out what can we start doing to address them. As we launched the sorter and started having thousands of cartons ride each day, we also faced the problem that sometimes there'd be a production issue. So in software production issue, when your site goes down, like as Stephen was saying earlier, someone gets paged, an engineer starts looking at the logs, they fix it, and that's hopefully job done within a few minutes. In a warehouse, when you've got thousands of boxes riding the sorter every day, you have a production issue, it's bad news because suddenly, instead of thousands of boxes going to a truck, thousands of boxes end up at your jackpot lane, which is on the second floor. There's 2 lifts to get down to and it's a nightmare. So we had to very quickly help teams that weren't used to dealing with these kind of production issues come up with a process that was organized, that worked in a similar way to how software teams manage a production issue to quickly get to the cause, work out some workarounds, and get the cartons flowing again. One of the ways we helped address this was by running some simulated failures. So we'd get people from the mechanical team, the operations team, the software team in a room together, and we'd simulate a production issue. And we'd get people to think through what would they do next in order to work around this issue or diagnose it. And those kind of fire drills are really, really useful to getting people in the habit of thinking, how do you address a production issue quickly and effectively. We also started running postmortems as well, cross-functional postmortems to help other teams learn from these issues. As we learned more about the impact that the operational staff were having, we realized that there was some basic training that people were missing, such as when you put something on the sorter, you've got to make sure there's quite a big gap between items. Otherwise, boxes, when they're really, really close together and they go through a scanner, it thinks they're a single box. Which causes all sorts of problems. So in the training for people that were working on the sorter, we made it clear, 30 centimeter gap, okay, that's what you need to do. Right, so that should be fairly simple, okay? That should hopefully address the problem. Well, I don't know if any of you have seen Stephen Shorrock present. He's an expert in safety critical systems and how we can learn from production issues. He spoke at Lean Agile Scotland last year, and he had this great quote: "The work as prescribed is rarely the same as the work that's actually done." When you look at how people work, they generally don't work in the way that they're told to work. They'll find shortcuts. They'll find easier ways of doing things, or they simply won't remember what they're supposed to do. And this inequality is what often leads to problems. So we needed to think, well, what can we do about this? We can't just keep training people because they weren't, learning from that training, weren't able to follow it. One way to address this is trying to reduce the amount of human interactions. But that is actually very costly. So we had to learn how can we keep the same level of human interaction, but give humans more agency in improving the system. So the way we approached that was we got each shift together, each shift of operational people. And we ran a workshop with them at the start of their shift. We asked them this one question. We gave them some data about the kind of issues that we were seeing. And we got them to consider what change can they start putting in place that's going to reduce the jackpot that we're seeing and that they can start doing tomorrow. We got them together in a room. We created a simple visualization of all the different types of problems, a bit like the pie chart we saw earlier. And we had the current jackpot figure written up on the wall. And we asked them to think, what kind of jackpot figure do you think they could reduce it to in a month? Some of them were quite optimistic. And we asked them to come up with some ideas. What things do you think they could do themselves, operational teams, to get down to that target? And they came up with all sorts of ideas, which was absolutely fantastic. And that, I think those workshops were a fundamental change in how they were approaching things. Because instead of just following instructions, putting cartons on the sorter, they suddenly had ownership and awareness of the impact that their behavior was having on the whole system and on customers, and also on their own kind of work and their colleagues. So what we saw as a result of this was a real reduction in these kind of failure modes, and principally from operations starting to kind of work more differently. So they were doing things like rotating people around different parts of the sorter. Previously, the same person would always typically work on one part of the sorter. And that meant they weren't aware of the impact that their actions were having on somebody else working elsewhere. Whereas by rotating people around, they start to learn, like between cross-functional teams, you start understanding, as a developer, the impact your work is having on a tester. And it made a massive difference. It gave people much broader knowledge. It made people kind of easier to kind of move around and do different roles. And we saw people thinking much more kind of, critically about the work they're doing, why problems were happening, trying to solve these problems themselves. So what are the kind of key things that we've learned from this? So whether you're working in cyber-physical systems or not, I think some really important lessons that you can take away, you can apply to the work you're doing. So firstly, think about the observability of your system. So when you're trying to improve its efficiency or optimize it in some way, or simply address defects, are you able to observe enough of your system and understand the relationships between the events that are going through your system, the key entities? Can you identify the key entities and follow them through? Do you have enough domain knowledge to understand how volume goes through your system? So when a product or a kind of event goes through your system, what's actually happening to it all the way through that can result in a problem? Consider as well your team. Do you need to make your team much broader than just standard devs, QAs, UX, and product people? Are there other people involved in your organization that have an impact on the success of your overall system? Consider also how you use data. So another thing kind of Stephen said that I really enjoyed this morning was about the importance of collecting data as early on as possible about issues, and then using that data to prioritize what you go after. Think about your incident management as well. So when you're next faced with a production issue, consider if there are people that aren't in your response team or aren't in your postmortem that actually could have helped solve the issue or contributed to the issue that you need to include. And finally, think about teams of people that are involved in your system that they may not be aware of it, or they may not have enough ownership of their part of the system that is contributing to some of the issues that you see. All right, thank you for listening. Do we have any time for questions?
Yeah, we've got a whole 6 minutes. So.
Great, excellent, thank you. Any questions?
Do you think the pain of the jackpot being 2 floors above where it should have been accelerated the need to solve the jackpot problem? Or do you think you would have solved it even if it wasn't so painful?
I think it did contribute, yes, to the urgency to address it. Because so for instance, in America, which is where a lot of the other warehouses were, they had it on the ground floor because space is cheap in America. You don't need to build up so much. So when they had things going to jackpot in America, it was always much easier to get it to a truck, whereas we were faced with a real kind of pressure. So yeah, that was a contributor. It was a controversial decision to put jackpot on the second floor because of that reason, because it made it so difficult to get onto a truck. But I think it was a good thing because it did force us to look at our processes and we got jackpot down from 30% to about 3% in that time.
I think it was really interesting. I'm just interested in the sort of lapsed time that was involved, because it sounds like you did some very thorough, detailed work, and I presume Equal Experts, you were the vendor, as it were, in this, and did you have a very patient client? Were they very patient for you to go through all these steps, and had they tried to solve it already? So what made them patient?
Yeah, good question. So you're asking about the elapsed time. So the sort went live in June. I'd been working on it for about 3-4 months. So although Equal Experts were involved, I was working as a technical program manager, so spanning multiple client teams and also vendor teams that provided the sort of system. I was helping glue all those teams together and lead the kind of diagnosis of these problems. They were patient. What they appreciated was seeing progress. So we had 5 to 10,000 items riding the sorter every day. We had about 30% jackpot in June, and what they appreciated was that they saw that we were diagnosing these problems, that we had a methodical way of working out how to address them. And it did take from June through to about April the next year to get down from 30% to around 5%. But they were seeing steady progress, and that's what they appreciated. The other thing that helped is that it highlighted that other warehouses in America were much worse than the UK one eventually, and that we became the leading light in how to improve your software sorter process.
I'm going to go here because it's closer.
Thanks, Lyndsay. That was very interesting to hear. I've been imagining the boxes going round and round, and all the things that might have caused the problems you were saying, because a lot of things about misreads and things like that. Are you able to tell us how you solved a lot of the different categories you saw there?
Yes. So one simple example was that some no reads were happening because the barcode had been generated by converting a PDF into a PNG, or kind of vice versa, and it was done at a very kind of low resolution. So the image that was printed onto the sticker was so blurry that the camera, because it was basically a digital camera taking a photo and an image and processing, it just couldn't distinguish the gaps between the lines. That was a very simple example. A more complicated example was where the what do you call them? Sorry, my brain's gone a bit dead. There was a way of templating what how to extract the tracking ID from the barcode, and the way that template had been written was incorrect, and we didn't realize that for quite a while. I think that the hardest bug to find was actually a bug in the scanner, where the scanner was reading the barcode fine and it kind of captured all the digits, but then in the communication between the scanner and another part of the software, it was dropping a digit. So you went from 11 digits down to 10 digits. And that was just down to a bug in the scanner that the scanner operators or vendor had a fix for, but it took us a while to identify that one. There's lots more I can bore you with later.
Yeah.
Yeah, thank you. I thought that was really interesting. I love that at the end, you found that the solution was actually making sure that the people, the operators, had agency. My question is, were you tempted to continue to perfect the system so that you didn't have to have any agency? And at what point do you say, right, well, this system is perfect and we have no need for any human sort of mistakes? And at what point, or how did you come to the point where you thought, okay, well, this is where it's going to be, and now we have to meet with that human agency, that human training?
We got to a point where we figured we'd identified, we knew all the software problems. Some of them we hadn't fixed, but we knew about them, and we still had 15% jackpot. And the data, as I kind of showed, was telling us that to get down to 5%, these are mostly operational issues. And part of the problem around the agency was it was a sensitive conversation. Let's put it that way, to explain to the operational teams that the way that they were working was leading to kind of a high failure rate, and giving them the agency to kind of solve that and empowering them made a massive amount of difference. And I wish we'd done that much, much sooner, like months sooner.
Is that why? So did you realize that it was more cost effective then to have the humans meet you halfway rather than saying, right, well, we're just, like, for example, if you said that there was a problem because they were loading the boxes on too quickly, rather than try to solve that problem and make the system so that it could handle the boxes too quickly, was it better at that point to just say, right, we're going to get the people involved and train them so that they don't put it on so quickly, rather than optimize the system?
Yeah, I think sometimes the cost of optimizing the system through software or mechanical changes was actually very, very high, and that actually training people and getting actually skilling up people a bit more to operate it more effectively was cheaper. A big a solution we also found, similar to software teams, if you have long-lived software teams, they tend to function better. It's the same with our operational teams, that at the start we had a very high turnover because we were using a lot of temporary staff in our operations teams. And that high turnover was just punishing us the whole time because you'd lose that knowledge. And once we started having long-lived operational teams that stayed together, that rotated the roles around the sorter, so we also saw improvements.
Thank you very much, Lyndsay.
Thank you.